My name is Ilya. I'm working for DataGrid. We do things with PostgreSQL support consulting, things like this. And today I will tell you about Linux I/O internals in relation to databases and in particular to PostgreSQL. So the name of this talk is Linux I/O internals for PostgreSQL administrators in 2020, which is quite typical for this topic because databases are generally very conservative in terms how they operate, because it's like complicated product and not easy to evolve. But currently Linux I/O stack is like under very intensive redevelopment. So many things are changing, and sometimes it doesn't affect database systems. Only the performance increases sometimes. Sometimes it requires different approaches from both administrators and from developers of database systems. So just a quick question. Do you consider yourself like a PostgreSQL DBA? Just raise your hands if you are like working as a DBA. Or another hand if you're just curious about I/O internals in terms of databases. Okay, so then we do that like this. I will not concentrate a lot on exact giveaways, like set this parameter to that and get this result, because it's slightly tricky, but DBAs like this approach sometimes. And we will talk about a bit more theoretical things just to grasp the full picture and give you a clue where to research and what papers to look into. So, why this talk, exactly this talk? Linux is most common operating system for databases. Good or bad, that's really some sort of eternal question, but currently it is like this. So we need to figure out how to work with databases on Linux. And I/O problems is a very common thing. So basically, there are different types of problems in databases, but I/O problems is very common. And they are not quite easy to deal with, because if you hit I/O limit, most likely it's difficult just to put new disks because those disks have limitations. So you need to figure out how to optimize this. But the problem is that most information on this topic is written by kernel developers. And that automatically means it's written for kernel developers. And being a DBA, you are facing the very tricky problem that you need to constantly to take a look on ulvn.net and monitor a couple of email lists and things like this, and basically learn to program in C and better to program kernel. That's not your job. You won't do this most likely. Another option is sort of checklist documentation. Like PostgreSQL documentation includes quite useful parts on how to optimize Linux for working with Postgres, but it's like this setting with recommendation like this. And that's not good idea, because sometimes situation change, your workload changes, and it's not easy to figure out in which direction you need to adjust those parameters. So I will try to combine those things in more useful manner. The main problem for databases in regard to I/O for a long time was how to maximize throughput of pages from memory to disk in both directions. And this is a very tricky problem, because it's not the problem of how fast your disk is. It's a problem about the entire I/O stack, because if you do not have enough CPU, it doesn't matter how many disks you have and how many memory you have, you just doomed, because without proper CPU, you cannot afford a lot of input-output throughput if we are talking about database, like a multi-process system with concurrent access and so on. And the same thing about memory, I/O schedulers, file systems, some database settings, like problems like log contention and so on. So basically everything is involved, and we need to balance the entire system to maximize this throughput. But I/O problems actually not only about disks and memory. So it's like network input-output things could be an issue as well, but we will concentrate on just isolated topic of memory and disks because it's easier to fit into one talk. The main reason why it is so why we tried to maximize throughput for years, is that at this point the latency was very significant. In times of rotating disks, it was impossible to improve latency here because like mechanical disks, they're not quite fast. And well, the entire approach was like this. Generally speaking, if we are talking about throughput and latency, throughput in databases is much easier to achieve because you can use some sort of parallelization, you can use a lot of disks, building arrays of disks and so on. So it's like, it looks like very good thing. But at some point you hit like last mile task and you need to improve latency as well. But now actually we have proper hardware to improve things. So modern SSDs, they are by definition quite fast, and which is more important, they give you a lot of parallel capacity. So basically on the hardware level you can utilize parallelism quite impressively. And another big question is, our old conservative database software, is it ready for that things or not? And another question is if Linux IO stack is actually ready for that. And we will try to figure out how it looks like. So because of this high latency of rotating disks, for years the situation was like both database developers and Linux developers were concentrating about the throughput. And those optimization techniques are actually quite obsolete in terms of SSDs. So basically we still can use some approaches, but the effect is like you cannot detect this effect sometimes. So we need some new approaches and figure out what sort of old approaches are applicable to our problem. So PostgreSQL database, just to remind you quickly how it looks like. It's a database which operates with data files on disks. Those data files consist of pages. If we read something, we just put that into the page cache. Postgres uses buffered input-output. And then we copy that to user space, to PostgreSQL shared memory, and if we change something, we just mark the page as a dirty page, write the information to the Redhead log, and at some point we issue a checkpoint which synchronizes all the dirty pages from shared memory through page cache back to the data files. So that's our workload. So it's like the profile which we need to optimize. Key things about such workload. It used to be much smaller amounts of shared memory than this system was initially developed. So now, then I started to talk about Linux and internals in regards of databases. I used to say 16 gigabytes. It's now it's affordable. Cheap amount of memory. Then I started to say 32 gigabits is affordable. Now is actually like half terabyte is not that uncommon in terms of memory. And then you have that amount of memory. You need actually learn how to work with this. So just simply this synchronization of dirty pages, it's a lot of input-output. Another problem is that a Redhead log, if we change a lot of pages, because today everyone likes big data. I never saw a person who likes small data. I personally don't understand this. I like small data, but well, maybe it's because of experience. But Redhead log is like the thing which should be written quite robust and quickly, and that's another source of headache and input-output problems. And for every of such task, the entire stack is involved. So basically, for write-ahead writing, we need everything optimized. For checkpoints, we need everything optimized. And besides of these, there are tasks like if we do not fit into work memory, then we perform some hash join, external sort and things like this. We go into the disk, and this is very inefficient. So basically, it can add some overhead to our general most valuable input-output operations, and that could be a problem as well. So first thing first, if we allocate memory to use our shared buffers, for example, or another part of Postgres, it's quite complex process. So basically, we have physical addressing in the memory, but our processors and entire operating system operates within the concept of virtual memory, because it's much more easier. Every developer likes the idea that memory is infinite. That's very convenient approach, but it has some problems, let's say. So to allocate memory, we need to go to memory management unit and then allocate this physical memory, and this process is called translation. So basically, we need to translate one address space to another address space, and this operation is not very cheap, especially if we have small chunks, small pages of memory, and large amounts of memory on our machine. So for that purpose, so-called translation look-aside buffer was invented, which is basically a cache. So we are caching inside TLB this operation of memory translation. And that's a very efficient thing, because we do not need to go twice to memory management unit to the memory, and that works good. But the problem is, if we have small pages in our memory to allocate, our translation look-aside buffer grows. It has some certain limits, but still it grows. And you can imagine it's just normal cache in this regard. So if cache is too big, it's really expensive to maintain this cache. We run into problems then we only once put the page in this cache and never get it back because it's too large. So it's lots of problems of typical cache. So for that purpose, the concept of huge pages was invented. So first optimization which we use normally if we have lots of memory and we need to improve entire I/O system is actually huge pages. We need to enable them in kernel, and we need to tell Postgres that Postgres should allocate shared buffers from huge pages. That brings lots of benefits, and the idea is very transparent. So basically we have more efficient translation look-aside buffer, and we can access shared buffers faster. So by default, if you have more like 32 gigabytes of memory for Postgres shared buffers, you probably like to use huge pages. Don't be confused with so-called transparent huge pages, which is more modern, more efficient mechanism of using huge pages. And actually, for many workloads, people advise to use transparent huge pages, but we would not recommend to use that for such workload like PostgreSQL with this huge chunk of shared buffers, because then transparent huge pages starting to merge, and other issues with transparent provisioning of its size gets involved. you can actually run into significant delays with operation with your shared buffers. So it's very inefficient to use with Postgres. So basic idea is enable huge pages, disable transparent huge pages, because normally it's like work quite good. At some points you're stuck into this problem of resizing and merging of transparent huge pages, and you have some delays which are unpredictable and quite difficult to diagnose actually. Another problem is not allocating memory but freeing the memory, and for database systems it actually involves lots of tricky things. So basically if we have generally the memory which could be used by our PostgreSQL, we allocate shared buffers from huge pages, and this is like a chunk of memory which is easy to use. It would never go to the swap, it's just allocated statically on the start of Postgres, and that's okay, that's not a problem. But Postgres needs memory for another operations, like for each process it consumes memory. It consumes memory for auto vacuum, for index rebuild, for hash joins, for sorts, for temporary, for many things. Here it's like huge room for optimizations. Linux in the kernel maintains so-called free lists. So basically, there are free lists which are like pages which are ready for allocation. And if we need, for example, some work mem for our PostgreSQL process, we call allocate, then we call free and return this page to this free list, and it is again ready for allocation. But it's in ideal world, because people tend to write bad queries, people do many stupid things, so sometimes the situation is we allocated something for our work memory and waiting, it doesn't get back because idle in transaction or something like this. What is going on in Linux in this case? There are two mechanisms actually. If we are starting to run out of memory and out of those free lists, we can page out some unused pages. So basically, if we have clean page, which is not dirty, we did not use that in Postgres for some period of time, it actually syncs in our buffer and it could be like freed. So page out daemon can actually put it to the free list back, and if we need this page immediately, it would be reclaimed back. So basically it's quite efficient mechanism. So we do not free this page entirely. We just say that it's ready to be freed and to be allocated. If this free list shrinks, this page would be ready to be allocated. That mechanism is quite efficient, and it's like the primary mechanism to free memory in this case. But if it's not very efficient, so basically we're allocating memory faster than we're supposed to do this, we can go to a swap. So basically if this thing is not very efficient and we hit min 3 kilobytes and this list is too small, we go to swap. That's good emergency measure, because if we don't go to swap, some bad things can happen. But for database performance, it's not very efficient, because swap is on disk and it's very slow. So you don't want to go to swap if you're talking about tile performance on database. So we need to figure out what to do with all those parameters. So there are some system catalog parameters which can regulate this behavior, and it's good to know how to use them. So page out happens in 3 cases. Then someone calls fsync. In PostgreSQL, generally it's rather checkpointer more oftenly, or background writer, or in very bad case, one and every PostgreSQL worker can call fsync, and that's very inefficient. Or if timeout is exceeded, or we have too many dirty pages in kernel buffer. So those parameters, dirty background ratio and dirty ratio, which by default are 10% and 20%. If we have this amount of dirty pages, we're starting to page out. And if we have some slow disks, it's reasonable to tune dirty parameters to something smaller things, because like 10% of entire memory in the system is like, it's a lot, and most of rotating disks cannot just afford this amount of I/O. With SSDs, we can leave that by default, or even sometimes increase, because SSDs are quite fast, and we probably can improve behavior of page outing by this parameter. But that still doesn't keep us safe from swapping. So for swapping, we actually have several options. The first one is quite simple, memory over commit. So operating system Linux can consider swap and memory as single virtual memory. And for database, it's bad. So basically, main approach is not to overcommit memory, because then memory goes to swap, everything would be slow. There is so-called heuristic overcommit. I don't recommend to use this, because you can never guess when your database would be in swap and then not. And it's even worse if it's constantly in swap, because it's constantly in swap, you know there your problem is. It's like drunk man method of finding performance problems. But that's a proper way. Mean 3 kilobytes. It's a good idea to keep it reasonably high. Why? Because if you take a look on this picture, it actually regulates the size of the free list. How many pages are ready for allocation in your free lists. So basically, if you know that your database workload is tending towards large sorts or large hash joins, you need a lot of memory to perform those operations. It's good to have this thing a bit larger, because memory allocation for new worker which starts to working with sorting, merging and hashing would be slightly faster. So it's good idea to improve that part. But you should like keep some sort of a balance, because if this thing is too large, page outing starts faster and your cache is not that efficient, your buffer cache is not that efficient, and you can end up in swap quite early. VM swappiness is another parameter which protects you from slowing your database down because of swap. Nobody understands how it works properly, so I tried to ask actual Linux kernel developers about this personally and never get clear answer actually. No? But from my experience, it's like better idea to set it to 1 if you use relatively modern kernel. So if you use 2 something like this, upgrade. If you use modern kernel, just put it into 1, because totally disable it actually increase the probability of out of memory killing. And if it is by default, that means if you have a lot of memory, you most likely will end up in swap, and that's bad practice. And last thing, your database would not like OM killer. So basically, if you know how many PostgreSQL workers you have, you know how much memory you have, you know size of your shared buffers, keep in mind that if you exceed this amount of physical memory with those settings about swap, you get your PostgreSQL server killed by OM killer. If you change those parameters to avoid this, you end up with bad performance. So there is no free breakfast here. So basically you have limited amount of memory. OM killer is actually a very nice mechanism. So some people keep asking if we can disable it. You couldn't, because it's a proper emergency mechanism. And if you take a look on most of methods how to disable it, it's like much worse than hitting the actual out of memory kill. So if out of memory kills your PostgreSQL, you have some information about this in your logs, and you can actually figure out, okay, we probably exceeded amount of memory and we need to take measures to avoid this. If you have these settings active, so if your Linux panicked on out of memory, sometimes it's not easy to figure out why it was so, because Postgres cannot write to its log, and you have difficult times to figure out what's going on. So my advice is actually use all those parameters like I described and calculate carefully not to exceed amount of memory. So basically, if you go to swap or if you go to mkiller, that's not about performance. It's like it's a problem. Another important thing in this IO stack is file system. File system generally today has a mechanism which is called barrier. So the idea is quite simple. We have journal-weighted file system. We write journal and we write data. It's okay on the laptop because we have relatively small page cache, relatively small kernel buffer, but if we have half a terabyte for a database, it's difficult because we have some journal entry, some data entry, and data entry is already on disk, and journal is somewhere up in our stack. So basically, if in this case we switch the server off or cut the electricity or something like this, we can lose potentially those data if something goes wrong. And Linuxes have mechanism for the file system called barrier. So basically, it's a system call which, in this situation, is fired, and at this point Linux starts to resort kernel buffer to get this journal information and put it to the journal in order to keep those things synchronized. So imagine a large kernel buffer with these constant resorts. Then for example, your checkpoint is active. So basically, it's permanent source of trouble and IO spikes and things like this. So basically, if you are using proper hardware like SSD with supercapacitor or old school RAID controller, you're supposed to disable this barrier. And it's much more efficient because you just move this safety mechanism to another level where it actually works. Because in case of barrier, it works on desktop or on laptop. It doesn't work with a database server. In terms which file system to use, it's like always tricky. I would say X4 or XFS are relatively good file systems in terms of performance. And which one is better is actually a very arguable question, and mostly about personal preferences. I know many DBAs actually like X4 because it's like more convenient to maintain, like resizing, things like this, managing free space and so on. Some people arguing that XFS is more enterprise, it can store larger files and things like this. So I would say like X4 is safe bet. If you have reasons to prefer XFS, use XFS. When we are talking about things like ZFS, things like this, they also could be quite good, but we are talking today about IO performance. So basically, if we are talking about IO performance, those file systems, because nice bells and whistles like dynamic provisioning of volumes and things like this, copy and write, that's not about performance for classical PostgreSQL workload. So it's very good to maintain, for example, development environment, then you need to clone some exemplars of database quickly. It's very convenient, but it's not about performance, so it's different tasks. So back to IO stack. So IO stack is like very complex thing, and we have our user space database memory. We have different interfaces how to access block layer, then we get our blocks. We need to form an IO request towards the hardware driver, and this layer is actually quite complex as well, because we need to optimize those vectors of blocks to be written or read in efficient manner. And it used to be like this for years, for many kernel versions actually. And important thing is that up to this level we operate with pages. Like this very convenient conception, like in databases pages are for many years, because it's easy to schedule transactions on pages model, so it's like very good. Then we operate with cylinders, sectors and things like this, which are totally bound to the rotating disks, to mechanical disks. And at some point here we need to make the transition from one to another, and most likely perform some optimizations, because if we are talking about cylinders or exact place on the disk, we need just to optimize those pages to go to the same place. So it was like the task for Linux developers for years, how to optimize those things. And for DBAs actually as well, because you know those tricks like we put index on this disk, we put data on this disk. So it's all was about those optimizations. Yeah.
Can you go back a second?
Yeah.
It seems like there's a missing abstraction there of blocks. Shouldn't that be in between sectors and pages?
Yeah, exactly. So it's actually part of this translation. So BIO, it's block input output layer. So basically we collect pages into blocks and then form IO requests from them. It's a good point, yeah. So long time ago there was only one only one IO scheduler. So basically to optimize those things we need some sort of a scheduler. It was called Linus Elevator, and it didn't work. And of course it was a beautiful piece of software because it was Linus Elevator. So basically the idea was very simple. If we know that some piece of the data resides on the sector of the disk, we need to put that together. So if we know this information about the data, we just merge in request queues and sort in blocks, and then they put everything to the disk, and voila, it works. It didn't, because like reads and writes were interacting with each other. There were lots of starvation problems and things like this. So basically, immediately people started to develop more complex schedulers to optimize this part. The most universal one was complete fair queuing. The scheduler which implements the idea of we have, for example, different processes, and each process has, based on process ID, on things like this, has its own input-output queue. And well, that's universal. That means it works bad. So it's good for example, desktop environment or for a laptop, because then you're writing some document, then you're at the same time you're listening to your music, encoding video. That probably would work in average not badly. But for a database is a very specific workload. It's like bulk amount of dirty pages you saw initial picture. So if it's like this, it doesn't work, because you generally get an average bad performance. So for databases, it's not good. Another idea was so-called deadline scheduler, which was based on a simple idea. We have read queue, write queue, and we have deadline queues. So basically, each request has its deadline, so some estimation of the time when it should be finished. And if we reach this deadline, we prioritize this input-output operation, and we like accelerate it. That was also not very efficient. Just imagine you have several queues from for passport control or for airport security or something like this. And some person goes around the queue and asks when your flight is. You say in 20 minutes. Oh, go back. We take another person in front of you. And that basically leads to the situation then everyone is practically missing his plane and then goes to the front of the queue. So it's not very efficient too. We used to use this deadline scheduler for rotating disks, but well, it actually not a very good optimization, and it definitely doesn't work for low latency storages like SanDisk arrays or EnvyMe, PCIe SSDs and things like this. So very interesting workaround was implemented that times NOP or none. So it's very interesting approach to the scheduling and basically disables all those optimizations. And it was like quite more efficient than previous two. For databases, yeah. I'm talking about databases in general, yeah. So basically, we put SSD, even SATA SSD actually, and disable this scheduling, and it works better. So after Linux kernel 3.13 in normal classification, not enterprise Linux kernels classification, version numbering, the effectiveness of NOP was like proved like it was very good, and people start to overhaul entire input-output stack. That ends up in so-called bulk memory queue, and it's actually incorrect to say that it is a scheduler. So basically, Volcom queue, it's very good invention in terms of databases and PostgreSQL as well. But it's not just a scheduler, it's sort of substitution of entire middle layer of input-output stack. So it's basically block IO level, request level things, and schedulers as well. And it has native parallelism, so it's much better for SSDs, it's optimized for SSDs, and it's very good improvement for databases. How it looks like. So it's basically substitute entire layer, and it has its own input-output schedulers. I would not stop in details on how efficient those schedulers are, but actually just substituting this thing to Volcom queue improves performance so drastically that probably you don't need to know this information yet. It comes together usually with EnvyMe driver. So basically, if you put an SSD into PCI Express, by default, it would be like this in model kernels. So basically, sometimes it shows that you have NOP input-output scheduler, but it's not true. It's just like sort of placeholder. It would be most likely Volcom queue. And then it started, we saw like improvements, sometimes 10%, sometimes 20%. Now actually it could be even more. So it's very efficient improvement for databases. So the general idea is instead of one hardware queue in the driver, SD driver or something like this, Volcom queue has multiple queues which corresponds to exact SSD. So basically it has input queue, output queue to the hardware, and basically if you have enough CPU, you can theoretically reach a very efficient input-output practically without any locking, because one processor actually works with specific queue, and that's end up in hardware queue. So basically, theoretically, everything sounds very good and very promising. And it is, but there are issues, as you can guess. By the way, of course, my diagrams were very simplified because it's like small talk, and we have not a lot of time to discuss those details. Here you can find a very good diagram of Linux I/O, which is regularly updating based on current state of affairs in Linux world. I will publish slides later, I think on Scale site, so you can use the link there. EnvyMe, a couple of words about EnvyMe. EnvyMe is a very promising technology. So basically, now you most likely don't want to use SATA SSDs or things like this. You rather use disk array or you use EnvyMe locally. And actually, local EnvyMe is maybe one of the most affordable and fast options you can get, because it's usually faster than disk array because it's like locally on, basically on your motherboard close to the CPU. And it works quite well. But the most interesting question, are the databases now EnvyMe ready? And that's the tricky question. So in terms of like improvements which are quite nice, and we would like to see the performance gain in terms of databases. Recently, EnvyMe and Volcom together, this entire system, has I/O polling. So latency was decreased to the state, then actually waiting for interruption from SSD became an issue. And that's why the polling mechanism was implemented, which reduced CPU load and reduced latency of disks. So it's like, it's very impressive improvement. There are no new I/O schedulers like Cyber and budget fair queuing introduced in new kernels for Volcom. Kyber is a very simple scheduler which is quite fair. So it's basically doesn't do lots of mathematics, and budget fair queuing is like very complex thing. There are lots of papers with descriptions of those mathematics, and the basic idea is for each I/O queue there is some budget of input-output tasks. To be honest, I do not see any difference in terms of PostgreSQL or while using Kyber or BFQ. Just Volcom gives a lot of improvements between different options within Volcom. I would not say I saw anything significant from DBA point of view. I/O tagging is a nice idea because if you have, for example, different containers or you have different virtual machines, each virtual machine can actually get more fair part of input-output, but it's not that relevant to databases. Direct I/O got a lot of improvements, and most interesting for PostgreSQL is actually a completely new thing, so-called I/O U-ring, which is like 1 year. 1 year ago, it was introduced in Linux kernel 5.1, and it's like different approach comparing to lib.io. So basically, it's 2 ring buffers which are simpler to use and which could be actually much more synchronous and much more faster than classical approaches like direct I/O. For like last important point for PostgreSQL, for years there was a struggle about direct I/O. So direct I/O is like used to be a very promising input-output approach, but it's not like perfect thing. And it's not always asynchronous, and it requires a lot of operating system specific code. That's why in PostgreSQL for years it wasn't implemented properly. Theoretically PostgreSQL supports direct I/O, but only for writing write-ahead log. And based on some issues with PostgreSQL architecture, if you need to use PostgreSQL in real applications, like you need to have a backup or you need to use a hot standby replica, it disables automatically a direct I/O for write-ahead log. Because if you open something with ODirect flag, you need to operate this file only with ODirect aware tools. And in PostgreSQL, you can basically use a hive command, which could be like a bash script, which knows nothing about ODirect and doesn't support ODirect, and this can crash your database. So basically, in Postgres, this was not implemented effectively. But now it actually looks like recent research on hackers shows that IO-ring is much more perspective thing in terms of improving EnvyMe support, BulkMQ support from the side of the Postgres. So I think it's like future, but in 2 or 3 versions of PostgreSQL, we will see even more improvements than just enabling BulkMQ and working with this. So that was it. Thank you for coming, and if you have some questions, probably we have time for 1 or 2. Or you can find me in PostgreSQL booth tomorrow on Saturday and Sunday before afternoon. I would be happy to answer your questions as well.
I have one question.
Yeah.
I was trying to get exactly direct.io is, I was like not finding, is there another name for it or something? I'm not finding results when I search online.
Well,
Intel direct data.io or?
direct.io implementation, which is within lib.io. It's a kernel, yeah. Yeah.
So Linux direct.io?
Yeah. Yeah.
Okay, good. Yeah, I see it.
So it's like it's very nice interface in terms that you can save on double caching. So in Postgres, basically, you read the block into the kernel buffer, then you use memcpy to get it to shared buffers. So it's overhead, it's extra syscall, and it's a lot of overhead actually. So
Just putting it directly into the kernel buffer?
yeah,
Okay. Thank you.
directly to the driver actually. Yeah. And you can use asynchronous I/O in this case. Theoretically, you can use OAtomic, which is low-level optimization of many SSDs, and you cannot use OAtomic, for example, without ODirect. Yeah, it bypasses the cache. Yeah, it just goes directly.
On a read, especially if you.
On write, it's even more important actually, because most of file systems support this, and actually from mainstream databases, Postgres is the only one which doesn't support ODirect. But the problem is most of the databases, excluding MS SQL Server, of course, they support like a very limited list of operating systems, and Postgres still supports lots of operating systems. At the same time, it's a benefit. At the same time, it's a problem. Yeah. More questions? Yeah.
So the direct I/O, I guess, works because you have a dedicated, I mean, the non-direct I/O can be called, right? It's for generic, like you said, the laptop where you're listening to things, you've got a lot of different I/O tasks going on, but if you just got a dedicated server dedicated towards Postgres, the direct I/O is beneficial because you bypass most of the OS stack, right, and go right to the driver.
Yeah, well, it's quite efficient because actually databases know a lot of how write data safer. So some extra layers are not that important.
Right.
Yeah, yeah. So
They become redundant almost.
yeah, they become redundable and they actually repeat one each other. So it's like. So thank you.